Môžem, hej? Good morning, ladies and gentlemen. Let me welcome you at our today's workshop, or 2 days workshop of Alexander von Humboldt Foundation project, which is called Embedded Optimal Control. On Monday, we will have 4 lectures, and then on Tuesday, we will have more informal discussions between the members of the project. So, who are the responsible persons for this project? Well, it's Professor Martin Mönnigmann from RU Bochum, and it's me, Miroslav Fikar, and Michal Kvasnica from our institute. And well, as I said, it's a project from Alexander von Humboldt Foundation between our two universities, Slovak University of Technology in Bratislava and RU University Bochum. So for today, we have two blocks for today. Both blocks are being streamed on YouTube and also recorded, so they can be watched later. And in the first block, I will start, or I already started with the introduction, and I will tell a few words about the project, how we thought it will work. And at the end, the last presentation will be by Michal and Martin to show us what actually happened, what we did achieve. And between them, we will have 2 lectures on from the German side, so from Ruth Mitze, the first one, and then the second one by Raphael Dyrska. Then there will be lunch break, and after lunch there will be 2 more lectures, one by Martin Klaucho and the last one by me. There are times here written, but I think this workshop is rather informal. So I thought something about 15 to 20 minutes of talk for everyone, and then discussion, but this can be longer, shorter. We have plenty of space to accommodate also some changes in both in the morning and in the afternoon. Yes, and also if you will not if you will forget where are those YouTube videos, you can go to our webpage of our institute and find it there. So let me start with first with the cooperation between our 2 institutes, and I can there are 2 decades, I would say, of cooperation. One in the last decade of the previous century, and then the other decade, which is now. So, as probably almost everything at this department in Bratislava, when we speak about scientific part of the department, it started with Professor Mikles. So, Professor Mikles was, or still is, Alexander von Humboldt fellow. He was in his first research stay. It was with Professor Oppelt. I think it was Darmstadt. I'm not sure about that, or Stuttgart or Darmstadt. I'm not sure. Yeah, yeah, and then just after the revolution, Professor Mikles went away for a few months from Slovakia, and he stopped at Bochum, at the IC building with Professor Umbehaven. I say IC building is the 3rd technological building at the RU University in Bochum, and you will understand why I stress it. And then also he invited both Professor Umbehaven and also his former PhD student, Professor Engel, who was just 20 kilometers far away from Bochum to visit Slovakia. They came here, and then Professor Umbehaven told me that I could also write the Humboldt proposal, so I did it, and I spent more than 1 year in Bochum with Professor Umbehaven. And then I'm not sure exactly how it went, but I think it was something like that. We were at the ECC 2015 in Linz, and I think that Professor Engel told me, today there is a dinner near the Danube River, come with us. So I went, and I sit in front of some guy I didn't know. Yeah. And we started to chat, and he said that he's from Bochum, and he sits in the IC building, yeah, at my place. And yeah, that the mechanical engineering department actually moved to this building. And we found out that we have quite many things common. We do model predictive control, and we found out that maybe we could write some small project. And that was also done in 2016. We prepared this embedded optimal control project and wanted to start, I think, from January 2017. But something got in the way, and we have to move for 6 months the project, starting from the 1st of July of 2017. And so before the project started, actually, Martin Mönnigmann was a plenary speaker at our conference, at the Process Control Conference 2017. And then the project started, and this is actually the last meeting of the project, so we will end in end of June of this year. And we started to work also on other projects. It's okay, there will be a little bit air, no problem. So we started preparing the Frontseat project, which is the Horizon Europe. And Martin Mönnigmann also started START project, which is a German project. And we are extremely happy to say that last week before last, we got acceptation for the Frontseat project, and that this cooperation will actually very smoothly continue, and that's what I am very happy about. So originally, this project was for 3 years, and it was about establishing research cooperation between our two departments in model-based control and optimization, and we found out that both sides have some advantages. So at our side, it was software development and geometric techniques of explicit MPC, and in Bochum side, complexity reduction techniques, online MPC, explicit MPC, and foster new cooperation activities. And actually this foster, this F, is a beginning of our Frontseat project. That F in Frontseat means fostering. So it really went that way. And there were also short-term visits of the young researchers and of senior researchers, and joint lectures and seminars. For the research goals, and this is always interesting to see after the project, so which of the research goals written in paper 4 years ago were actually accomplished. Yes, so some of them were, for example, we have nice results and presented today on reconfigurable explicit MPC, even if I thought it's not doable. Yeah? I thought that we will not solve this problem. Reduction of memory footprint, we did quite a nice work. Separation between server and embedded device. Safety of MPC, I'm not sure if we have so many new results. Application on embedded devices, yes. Even if I don't think that we worked on FPGA since Deepak Ingole left our department. But last week we had a nice, or Michal Kvasnica had a nice paper published with Deepak on FPGAs. We bought an inverted pendulum from this project, and we also tested, or well, not inverted, but we bought the Furuta pendulum. And we found that it's not so easy with this pendulum to work on. And for software development, the aim was to generate PLC and FPGA. There also, I don't think that we had so many new results. And for the conferences and workshops, we thought about 2 process control conferences. Actually, we got 3, but I will not tell what was happening. I will stick with this. Actually, the first event was summer school. I think Ruth, Yannick, and someone, Sebastian and Rafael, yeah, went to this. And to have MPC workshop at the process control conference and invited session at the process control conference. So that is for beginning from me. And I don't know if you have any questions or comments. Maybe for this meeting, if anyone from the audience will have something to say, please take the microphone, because otherwise people on YouTube will not hear you, or the speaker should repeat that question again, so that it is recorded. Fine. So if not, I think Ruth is the next. So please let me introduce Ruth. When do you finish, Ruth? Your PhD? Okay, fine, so let me have a small break. Ruth, I will give you the microphone. Put it aside.
Might know me, so I'm very happy to see you again face to face after the pandemic. So I will tell you something about active set enumeration for symmetric, constrained, linear-quadratic optimal control problems. So we will first take a look at the problem statement. Here is the classic linear-quadratic OCP, which you are very familiar with, I think. So we minimize a quadratic cost function, which minimizes states and inputs. And we consider a linear time discrete system. And we also consider linear constraints on states, inputs, and the terminal state. So the sets X, U, and T are compact full-dimensional polytopes. and the initial state x0 is supposed to be given. So the explicit solution of these kinds of problems is well known. It's a continuous piecewise affine control law. So the state space is divided into polytopes P, and on each of those polytopes, a control law of the form kx plus b is valid. Each control law and corresponding polytope can equivalently be defined by a unique active set. And so we can also express the explicit solution by a set of active sets. I will come back to that later. So in this presentation, we consider symmetric constrained linear-quadratic optimal control problems. And an optimal control problem is said to be symmetric to the pair theta omega if these conditions hold. So many times we can see the symmetries of the optimal control problems. For example, if we have symmetric box constraints, we can guess that it's point symmetric or rotational symmetric. If we want to find all symmetries, there is also an algorithm that we can use for that. So every symmetric pair theta omega also influences the explicit solution. So if we take an arbitrary piece of the explicit solution, for example, the polytope pi with optimal control law kix plus bi and optimal active set ai, and we also consider one symmetric pair, theta omega, then there exists another polytope in the solution, the polytope theta times pi. So this symmetric pair causes a transformation of the state space with theta. And the optimal control law is omega times kix plus bi. So this symmetric pair causes a transformation of the input space with omega. And we have a permutation of the active set ai with function pi. And last time, on my last talk, approximately 1 year ago, I already introduced this permutation function pi, and we used properties that active sets that are mapped with pi have in common to improve the dynamical programming approach that develops the explicit solution. So in this presentation, I want to again focus on this function pi and how we can improve active set enumeration approaches with that. But this time, I want to focus on the combinatorial MPQP approach proposed by Gupta, which is kind of the basic active set enumeration approach. But let me first introduce symmetric active sets again. So consider we have an optimal control problem that is given, and we have a symmetric pair theta omega. The OCP can be reformulated as a quadratic program with inequality constraints GU lower equals E x0 plus W. Then for every inequality constraint with index I, there exists another inequality constraint with index j, such that these conditions are satisfied. We will take a look at this statement more closely with an example. So suppose our given optimal control problem is symmetric to this pair of matrices. This particular pair of matrices causes a rotation of the input and state space by 90 degrees. Also, suppose that the first 4 inequality constraints of our quadratic program are those given here. Then, according to the statement, for every constraint I, so for example for the first constraint, there exists another constraint such that these conditions are satisfied. And this applies to constraint number 3. So in our function pi, we store that constraint number 1 is mapped to constraint number 3. In the same way, the conditions for the second inequality constraint, these conditions are satisfied for constraint number 4. So constraint number 2 is mapped to constraint number 4 by this symmetry. If we continue this for all constraints that we have, then we get a mapping again on all constraints of the optimal control problem. And by this, we can map active sets. So if we consider an active set, for example, the active set 1, 4, and we have this function pi, then 1, 4 is mapped to 3, 1 with this function. 1 is mapped to 3, 4 is mapped to 1. And the order doesn't matter, so 3, 1 is the same as 1, 3. We call two active sets that are mapped by a function pi symmetric to each other. And we could show that active sets that are symmetric to each other have similar properties. For example, if we know that one active set is element of the solution, then we know that all its symmetric active sets are also element of the solution. And in the same way, if it is not element of the solution, then all the symmetric active sets will also not be element of the solution. So we will now use this knowledge to improve the combinatorial MPQP approach from Gupta. But before we do that, I will give a short introduction into this approach in case you are not familiar. So the goal of the approach is to determine the explicit solution as a set of active sets. So if we remember the statement from the beginning, then our goal is to calculate all the active sets that define an affine piece in the solution. The combinatorial approach works with a combinatorial tree. Here we can see a combinatorial tree as an example with 4 constraints. So the combinatorial tree contains all possible combinations of constraints and therefore all possible active sets that exist. And we now want to identify those elements of the tree that are element of the explicit solution. Therefore, we proceed each element of this tree and test if GA is of full rank. If it is not of full rank, we know it's not element of the solution and we can discard it. For all remaining active sets, we use a linear program to test if this particular active set is element of the solution or not. As you can imagine, if we have a long prediction horizon and many state and input constraints, we have a lot of constraints and therefore this tree becomes very large and the computational effort is very high because we need to solve so many linear programs. So Gupta invented a pruning strategy. So if we detect an active set to be not optimal, so not element of the solution, we can solve another linear program called LP2, and by that we might detect many active sets at a time that are known to be not element of the solution. So we will now take a look at this symmetric, at this combinatorial tree, but now we want to consider symmetries of the active sets. So consider we have an optimal control problem with 4 constraints. So this is the combinatorial tree. And consider our problem to have 4 symmetries, 4 symmetric pairs, theta, omega. And consider the functions pi that results are those given here. Then for every constraint, so for example, constraint number 1, we can calculate the symmetric constraints. So constraint number 1 is symmetric to 2, 3, and 4. If we continue this for all other elements of the tree, we can see, for example, that 1, 2 is symmetric to 1, 4, 2, 3, and 3, 4, and so on. And as a result, the whole tree is divided into sets of symmetric active sets. And we call these sets of symmetric active sets orbits. So all elements of orbit 1, shown in yellow, are symmetric to each other. All elements of orbit 2 are symmetric to each other, and so on. So now let's remember the properties that symmetric active sets have in common. So if we know that the active set 1 is element of the solution, then automatically we know that 2, 3, and 4 are also element of the solution. And in the same way, if 1 is not element of the solution, the remaining symmetric active sets are also not element of the solution. So it is sufficient to test the active set 1 to be element of the solution in order to get a result for all other symmetric active sets, so we don't have to test them anymore. If we continue this procedure for all the other orbits, then we need to test only 1, 2, and we don't need to test 1, 4, 2, 3, 3, 4, and so on. So instead of testing all 16 elements of the tree, we only have to test 6 elements. We could show that if you always test the element of an orbit that is located most left in the tree, and if you don't test the other ones on the right, then we could show that for every element that does not need to be tested, all the child nodes also does not need to be tested. So this is symbolized by those scissors because we can cut the branches. And now our goal is to use this to improve the combinatorial MPQP approach that I just presented. So this is again the approach that I already introduced. But now we have those symmetries, so now we have those orbits in the tree. And the algorithm, again, first discards all that are not of full rank, because a rank test is very cheap. But before we test the remaining active sets with the linear program, linear programs are more expensive, we cut those branches that we don't need to test. So we discard any active set that is symmetric to an active set that was already processed. As a result, we hopefully need less linear programs, which we will see later in the example section. But we also only get a subset of the solution. So at the end, we need to complete the solution by adding all symmetric active sets to the solution. So for this particular example, you might see that there is a 90-degree rotational symmetry. And so we have 4 symmetries. And yeah, we need to add all those. So let's look at 2 examples. The first example system is shown here. It has box constraints. And as you might see from the constraints, it might be 90-degree rotational symmetric. And it is 90-degree rotational symmetric, so we have 4 symmetries. So this would be a rotation by 0 degree, 90 degree, 180 degree, and 270 degree. We will analyze the computational effort of the classical combinatorial approach and the approach that we just improved for problems with symmetries by listing the number of linear programs that are solved, because our goal was to reduce this number, and also by comparing the computational time that it needs. So the number of LPs for this problem was 12,000 for the classical approach and roughly 3,000 for our improved approach. So this is a decrease by a factor of 4. For the computational time, the reduction of the computational time is less. It reduces from 90 to 30, so roughly 66% only. We can explain why this reduction is less big if we take a look at the two algorithms again. So if we compare those two algorithms, we can see that both have the same overhead because all elements of the tree are tested for having a full rank. Then our improved approach has an additional step because we need to discard all those that are symmetric to another one that was already processed. And then we hopefully we do have less linear programs that are solved. So this is why this reduction is less high than this reduction. If you remember my talk from 1 year ago, I used to improve the dynamic programming approach for problems with symmetries. And for this example, also the reduction for the linear programs is 74%, so roughly a factor of 4. And the reduction in the computational time is 69%. Let's look at this second example. The system is given here. The state and input constraints are set to octagons. The origin, their middle is at the origin, and for the state space, the diameter is 20, and for the input space, the diameter is 2. So this example has 8 symmetries, so rotations by 45 degrees. The number of linear programs reduces by 87%, which is roughly a factor of 8. But the computational time reduces only by 24%. So this is much less. And if we take a look at the numbers for the dynamic programming approach, the number of linear programs that are solved also reduces by a factor 8. But the computational time only by 44%. Now I will come to the conclusion of my talk. So we again took a look at symmetries in active sets. Remember the function pi and also the symmetries in the combinatorial tree. Remember those orbits and the properties that the active sets in the tree have in common. Then we improved the combinatorial MPQP approach from Gupta for symmetric programs. And we analyzed the computational effort with examples. So the number of solved LPs reduced by the same factor as the number of symmetries of the problem. But the reduction of the computational time was less high than the reduction of the solved linear programs. Thank you very much for your attention.
Time for discussions. Anyone willing to start? Carlos?
Hi, Ruth. Thank you. Okay, this is fine? I think, okay. Yeah, and I think it's a quite really nice presentation. I saw you the last time. I really like this explicit NPC. However, I have a lot of questions here because I'm working with sonotopes and I'm working with polytopes and so on. And basically what we're trying to achieve is a sonotope. And a sonotope is already well defined, and we have the symmetries and the computational time. It can be reduced faster. So maybe have you considered to use, instead of polytopes, use sonotopes instead, and to get the same approach? Because for example, one of the things is that you said even if you don't have a symmetric constraint, you can have you can build someone, right? You can build and this when you build it, what you are doing is building a sonotope that is going to be over approximating the feasibility region. So you're going to lose accuracy, and although the problem of the pruning, can you guarantee that you always reduce the CPU time? So just to sum up, have you considered sonotopes as a computation? And two, can you guarantee that you are going to always reduce computational time? Because I thought you have very different CPU time. And yes, I have some other parts.
Okay, I will start with your first question. So I did not consider them yet, but yeah, we might talk about this later. Sounds interesting. And the second question you had, I cannot guarantee that the computational time is always reduced. But of course, I can guarantee that the number of LPs is always reduced. And I guess the computational time also always depends on the code quality that you have. So I did my best in implementing it and implemented in, using logical vectors and vectorization and so on. But this is not, of course, not the best that you can do. So yeah, I cannot guarantee a reduction in the computational time, but I can guarantee a reduction of the number of LPs.
Okay. That's really nice. And once more, is about the GA. Why do you check if it's full rank or not? Or can you talk to me a little bit more about why do you take the rank of this matrix, like if or not in a good way to reduce or to approximate the symmetries? If I get it well, I'm not sure. Is the G sub A?
Mm-hmm. So your question is why I check the rank for all elements of the tree and not...
No, for the GA only. The GA,
yes.
It was the whole element, right?
GA is only, for example, if the active set is 1, 3, then I would check the rank of the first and third line of the G matrix of the inequality constraints.
Okay.
I didn't introduce this notation.
What are you looking for on this? I mean, what is the rank that you're looking? I mean, you are not looking full rank. You are looking full rank in a matrix. I mean, if you have 2 constraints and you have only 2, and you have 4 dimensions, mm-hmm. you cannot check full rank because you only have 2 constraints and you are working in dimension 4. So the maximum that you can get is 2.
Yes. So I check of the rank if the rank of GA is equal to the number of constraints. So, for example, if I have 2 constraints, I will check if GA has rank number 2.
Okay. That's all for my side. Thank you.
Yes. Thank you for a nice presentation. And my question is, how expensive is to find the symmetries? Sometimes it's given by the constraints, I guess, mm-hmm. and then it's not maybe so difficult, but sometimes it can be maybe hidden. So mm-hmm. how expensive it can be?
I cannot really answer that because the examples that I looked at, I already knew the symmetries. Therefore, I refer to that algorithm from Danielson because he invented an algorithm for doing that. What I think is one more. Yes. So I didn't look at that in detail, so I cannot really answer that question. But most of the time, you can see from the constraints what are candidates for the symmetric pairs. For example, 90-degree rotations, and then you can check if those rotation matrices also satisfy the symmetry of the system and the symmetry of the cost function matrices, which were stated on one of the first slides.
Thank you, Ruth, for a very nice talk. I would like to know, is it possible to construct the tree in a symmetrical way? Because when I look at the regions, I see, okay, this is symmetric. I can directly see it, but is it possible to see it also in the tree? Because it was not so clear.
Yes, I couldn't find a way to build this tree in a symmetrical way. So the only criterion I could develop is those scissors, how to cut branches. But I'm sure it would improve the algorithm a lot to build the tree symmetrical right from the beginning. But I couldn't find anything on how to do that.
Yeah, that was my thought. And second question, what if the problem is not symmetrical, for example, constraints and so on? So if I normalize it, then I will get symmetrical regions, and if it is not normalized, then there won't be, or how is it? What is your experience?
If there are no symmetries to the problem, then you would have just one symmetric pair, which would be the identity matrix for the theta and omega. Then you can still use this algorithm, but it's better to not.
But if I somehow normalize the constraints so that it is symmetric, then I will have the symmetries in the problem?
I don't think so, but I would need to take a look at it again.
Okay, thank you.
Juraj?
Also, thank you for a very nice presentation. I have two questions. My first question is focused on the time evolution. Why it is that important, and what is the bottleneck from the implementation point of view?
You mean what does cause most computational effort? Yeah, so normally solving the linear programs takes most computational effort. So a reduction of them is most important. But as you could see from the second example that I showed, where we had so many symmetries, then the function to check if we need to consider that specific active set or not takes a lot of time. So then that function would be the bottleneck.
And what is the structure of this function? It is some set of if-then-else rules, or how it is built?
Yes, so if I go back to the combinatorial tree with those scissors. Yes, so for example, we process this combinatorial tree from top to bottom and in each line from left to right. So this way we always proceed the active set of each orbit that is located left first, and so we can use this criterion with the scissors. So for example, if we proceed the active set 1, then we would store all symmetric active sets 2, 3, and 4 in a matrix. And if we process the second one, then we would check if constraint number 2 is element of this matrix or is a child node of an element of the matrix.
I see, thank you. And the other comment, would it be possible somehow to introduce the parallel computing in the sense that once I have origin, the template of the critical region, then I delegate it to the parallel evaluation of its symmetric rotations, and simultaneously I am continuing in solving LPs to save some time. Do it in parallel.
Yes. I'm not sure.
Okay, thank you very much. Thank you very much for a very nice discussion, for all the questions and answers. And I think that's also the close of our first part before the break, right? Yes. So thank you very much.
Thank you.
Before the break, could we take the picture together, please?
Okay, what do you want? To have us here or there? Or morning session, and I would like to welcome here Rafael Dyrska. And please go on. The floor is yours.
Okay, so yeah, welcome to my presentation. I think most of you already know me from our previous events. For our final workshop, I prepared a presentation on simplified nonlinear programs for NMPC based on active set construction. And this is a paper of mine I submitted to this year's CDC, so hopefully some of you will see the same presentation again in December. Let's start with a short introduction. Here we can see a schematic state space with an initial state x0 and a terminal set tau, as usual for nonlinear MPC problems in the form of an ellipsoid. Now, if we solve our optimization problem, we determine an optimal input sequence, capital U, and a corresponding state trajectory, which ends in the terminal set, such that x5 here is our terminal state xn. Now, in the next time step, if we solve our optimization problem again for the new initial state, we actually don't know what the trajectory will look like. So it could be, for example, the black one here, but also the green one or something completely different. And there exist certain rules for the linear case, for example, the terminal or certain conditions, for example, the terminal inactivity, which make it possible to predict the open loop trajectory of the following time step, but this is in general not the case for nonlinear MPC as we treat it here. However, if we know the solution from the previous time step, we can construct a solution for the next time step that is at least feasible with respect to our optimization problem. And we can do this by using the tail of the previous solution, which is U1 to U4 from the blue one, and by extending it by applying a terminal control law, which a stabilizing terminal control law for our former terminal state, such that our new terminal state, xn here in red, will result by simply evaluating our nonlinear model to control. Now we have a feasible solution for our new initial state based on the previous one, and I will now show you how we can use this to construct candidate active set in the remainder. But first, let's have a look at today's agenda. I will start with a problem statement and some preliminaries, and then explain how we can construct active sets based on this previous solution. Then I will continue and introduce how we use these active sets to simplify our nonlinear program and show the benefits within the results of a computational study at the end before concluding my talk. Okay, let's start with the basics. In nonlinear model predictive control, we have this classic optimization problem or nonlinear program, or NLP for short, with the terminal and stage cost you are all aware of, with weighting matrices Q, R, and P. And we solve this problem for a finite horizon n and for a given initial state x0. We have equality constraints in form of our system dynamics F and constraints on states, inputs, and the terminal state. And as I introduced before, we will also use a stabilizing terminal controller, which will give us an input which respects the constraints on U and will also leave the terminal set positive invariant. The constraints on states and inputs will be noted by lower and upper bounds in the remainder, and we will also introduce at the beginning an ellipsoid as a terminal constraint, such that our terminal constraint will be represented by only one additional constraint. Now, by condensing the optimization variables x and u to a new optimization variable z, we can state the problem in a more compact fashion with the equality constraints collected in F and the inequality constraints collected in G, such that in F we have the prediction of our system behavior, and the inequality constraints, as introduced before, are summarized by G, and we will order them stage-wise. That means the constraints on x0 and u0 appear first, then the constraints for time step 1, and so on, and we conclude with the terminal constraint, because this order will be useful for us to construct our candidate active set. Now, you're also all aware of the active and inactive set, which are the sets of indices I corresponding to a certain line of G, such that this constraint for our optimal solution Z star is fulfilled with equality or strict inequality, and we denote the number of all constraints by Q. Beside this representation as an index set, we also introduce bit tuples, which represent all Q constraints, where a value of 1 corresponds to an active constraint and a value of 0 corresponds to an inactive one. So if we have a look at our inequality constraints, we can have, for example, an active index set with constraints 2 and 11. This will result in this representation alpha, and we see that also the order is consistent. We start with our constraints on x0 and u0 and conclude with the terminal constraint, and each sequence of bits corresponding to one time step here, each stage is separated by a dot. Okay, now how can we use these, how can we construct our active sets based on the previous solution? As I said, we have this blue solution here for our previous time step, and of course we can determine an active set for this blue solution here in both by writing an index set or also as representation alpha. And I said we can construct also a feasible solution based on the previous one, here shown in red, which was determined by using information from the previous solution. And now we can not only use the solution itself, but we can also use the active set from the previous time step to quickly determine an active set for the feasible solution of our new current time step, here denoted in red. And we do this by deleting the first stage of the blue solution, shifting all stages but the last one step forward, and inserting a stage of inactive constraints for the former terminal state. Now, one condition applies here. As I said, what we want to do, we construct a feasible solution by extending the previous one with the terminal controller, and then we want to construct an active set based on this feasible solution. So we don't really need this feasible solution, but this is something I will explain later. However, if we want to determine the feasible solution by applying the terminal controller, we have to distinguish between the case that the terminal constraint of the previous solution was active. That means the terminal state ended on the boundary of our terminal set tau, because if we then apply our terminal controller, we cannot really predict if the following terminal state will also end on the boundary or maybe in the interior of our terminal set. We can, however, if we know that the former terminal state ended in the interior of tau, then also by applying the terminal controller, the subsequent time step will end in the interior of tau. And then we know that also the terminal constraint for the next feasible solution will be inactive. And for a proof of the statement, I would like to refer to the submitted manuscript. So now we can construct a candidate active set based on the previous solution. And I will show now how we can use this to simplify our nonlinear program to solve. Let me sketch the main idea. Basically, the active set defines a solution for the nonlinear program. In our non-convex case, it's either a local or a global minimum, but that is not that important at the moment. And if the active constraints are known, we also know the inactive ones, of course. That means we could skip the NLP and directly solve the KKT equations. That would mean we would first solve the set of nonlinear equations and then check the Lagrange multiplier and slack variables if it is indeed a feasible and optimal solution. However, the solution of the KKT equations can be pretty demanding, and on the other hand, the solver for nonlinear optimization problems are becoming more and more performant. So instead of solving the KKT equations, we propose to simplify the nonlinear program, and we do this by knowing that inactive constraints have no influence on the optimal solution, such that we set constraints that are active according to the candidate active set to equality constraints and remove inactive constraints completely from our optimization program. Now, we have seen that if we solve the KKT equations, we have to check the Lagrange multiplier and the slack variables. And I always say candidate active set because also for this simplified procedure, we still need to check if the solution that results for the simplified NLP will not violate none of the original constraints. But I will show you this now in more detail. So we have our condensed optimization problem. And now that we have a candidate active set, we can rearrange the equality constraints. So we split G into equalities and strict inequalities. As I said, the inequalities, the inactive constraints have no influence on the optimal solution. So we remove this part, and a simplified nonlinear program results with much fewer constraints. And, well, of course, the need to check the original constraints. Now, what about if we have disturbances? We constructed our feasible solution for the nominal case so far. So we knew the successor state and could construct this feasible solution and then construct also the candidate active set. However, if we have additive disturbances that affect the states, for example, the closed loop trajectory of the disturbed state x0 tilde here in green could look completely different than our feasible prediction. So it's some deviation. However, as I said, we use this active set. The active set is in general valid for a set of states, or in the nonlinear case for one or more regions of the state space. That means all states in this blue region will result in an optimal solution with the same active set. And of course, also our candidate active set, if it leads to an optimal solution, then it will be also valid for a set of states. And that means even if disturbances apply, there's still a chance that this disturbed successor state will still be part of this constructed candidate active set. And yeah, I have to admit it is hard to quantify, but this regional characteristic of active sets gives us some degree of inherent robustness against disturbances. And the effect was already exploited for the linear case at the last IFAC World Congress and is now here transferred to the nonlinear case. And this regional characteristic is also the main advantage in contrast to simply reusing the open loop solution, because here we have an optimization again with the simplified nonlinear program and can thus react to disturbances. So let me quickly go through the proposed algorithm. We start with our current state x and our active set from the previous time step, here denoted by x minus. And if the terminal constraint was inactive for the previous time step, then we can construct our active set, simplify our NLP, solve it, and if a solution exists and the solution respects all of the original constraints, then we can apply the solution to our system. Otherwise, if no solution exists or maybe some constraints are violated, we have to solve the conventional NLP. Also, if the terminal constraint was active, then we cannot quickly determine the candidate active set. Then we also use the conventional NLP. And we see that we do not reduce the worst case computation time, but I will show you in the results section is that we can reduce the average computation time, which can be important, for example, if we have embedded devices with limited battery capacity. Okay, and this I will show you now. We applied the approach to a discrete time nonlinear system of a laboratory helicopter test bed with 3 degrees of freedom. We have 4 states and 2 inputs. And yeah, the parameters are listed here for completeness. For the system, we also have state and input constraints. And of course, again, terminal constraint in the form of an ellipsoid. And as we did with the constraints, of course, also the weighting matrices are chosen for from the corresponding publication. The simulation setup looks as follows. For 100 randomly chosen feasible initial states, we regulated every state for 30 time steps and compare the computation time and the number of solved full NLPs. That means NLPs which without modification for our proposed method and for conventional NMPC. And we do this for 3 different disturbance ranges, varying from 10 to the -1 to 10 to the -3. Here we can see for one of the initial states the state and input results and the computation time. The conventional NMPC is shown in color. Our approach, the results from our approach are shown in black. And we can see from the 2 upper plots that the results are almost identical. However, we can see in the 3rd plot that the computation time is for most of the time steps below the one that would result for the conventional NMPC. So here we can see that we save some of the average computation time, and that can be beneficial for us. If we look at the results, here we can see the number of full NLPs. As I said, that means NLPs without modification. And in the lower row, we can see the reduction of the computation time in %. And if we look, for example, for the large disturbance, we can see that the number of full NLPs decreased by 93%, which resulted in a reduction of computation time by around 10%. And these numbers increased for a smaller disturbance value, of course, because the feasible candidate active set was closer to the one we would have for the conventional NMPC. Now, we also checked how close our input signals resulting from our method are compared to the conventional NMPC. And if we look at the mean value, we can see that the mean deviation between the absolute input signals is quite small. If we have a closer look and look at the median, we can see that on the one hand, the large deviation here resulted for the large disturbance. So we can see we have a deviation in input signals of the absolute value from around 50%. However, we can see that this one is a statistical outlier when looking at the median. And on the other hand, I want to state that although we have this deviation of almost 50%, the solution we applied by our method was still an optimal solution, but simply another local minimum we applied to our system because we solved this optimization problem. And of course, if a solution exists that satisfies the original constraints, then it's still an optimal solution and also a valid solution. So yeah, these are the results for the method. And then I can conclude my talk. I showed a way to simply construct candidate active sets. And I want to state again that for the construction of the active set, we don't need to construct the feasible solution first, but we can directly determine the candidate active set based on the previous active set. We use this candidate active set to simplify our nonlinear programs. And we have some inherent robustness that is beneficial for this approach against additive disturbances. Future research will focus on the application to real hardware and investigate if weaker conditions on the terminal activity can apply to quickly construct the candidate active set. So thank you for your attention. That's it.
Okay, I will start. So I think I have 3 questions. First one, do you need some sort of assumptions regarding the model you can use in your nonlinear MPC? Or
basically not. So if we have our terminal, we don't even need the terminal control law, in fact. It was just for explaining how we construct the candidate active set because we don't really need to construct the feasible solution first. So basically, not more as the standard assumptions.
Okay.
I would say.
Okay. Second, how do you actually solve numerically those NLPs? By what method
it was done
solver?
with FMINCON, with interior point algorithm.
Okay. Okay, and the last one, I believe it was on the slide 60, but I'm not exactly sure. So if you can just jump back. Yeah. These blue and red regions you sketched here, is it possible that they will overlap? And if yes, can it create some problems or not?
Well, in general, for nonlinear MPC, they can overlap, because I think if we have, for example, for this point here, two local minima, so one with this active set, one with another active set. But for this method, it should not be a problem, because the same active set would result also as a local minimum for the solution. So if we find a solution, and this is a local solution with this active set, then it's okay.
Okay, okay. Thank you very much. Yeah, that's fine.
I think we have strong conditions on the example, not so much on the dynamics, but on the existence of the terminal controller. Even though you don't need it when constructing the solution, we need to know it, because we need to be sure that the closed loop system with the terminal controller is positively invariant on the terminal set.
Okay, well, we need this terminal set in our terminal weighting matrix, and of course the terminal controller to construct the terminal active set. That, yes, I only meant for the example system itself.
Thank you for a very nice presentation. Please, can you go to slide 63 where you present us your algorithm? Yeah. Is it really necessary to solve the full conventional nonlinear linear program here? Isn't there any heuristic analogous to the active set method to add just some critical constraints, for example, based on the Lagrange multipliers, dual variables? If you really need to solve the full complex NLP.
I'm not quite sure if I understand the question correctly. So we solve the conventional NMPC only if our method fails.
It means that there is some constraint that was found infeasible. So you should add some other constraints. And my question is, if you really need to add all of these neglected constraints, or you should select some smart order how to add them.
Okay, so I did not investigate it so far, but I think it may be a good idea for an extension. So we just add the constraint that were violated, if I understand correctly.
And also I have a related question. How did you find some robust nonlinear control that fits or holds inside your ellipsoid?
Well, it's not a robust terminal controller. It's just one stabilizing controller inside the terminal set, comparable to the LQ controller you have in linear MPC. So you needed to construct the terminal set. So you have a stabilizing controller. There are some heuristics, but there are also, you can also try to find a stabilizing controller. Here it was taken from the example publication. But you in general know it if you have a terminal set. You also need to construct the terminal controller to.
Thank you. And very last question: are you checking both the primal and the dual feasibility here in your algorithm?
It's a full optimization. So it's. This slide with the KKT equation was just for motivation.
Okay, KKT, so it means also the dual variables. Okay, thank you very much.
Thank you, Raphael, for a very nice presentation. I have 3 questions. The first one might already be redundant. So just to clarify, do you assume positive invariance properties of the terminal set?
Yes.
Okay. But that's quite difficult then to design, especially for generic nonlinear systems, right? So do you have any hints on how to design, or maybe even how to check positive invariance of a given terminal set?
Well, for the construction, I think you first determine your the terminal weighting matrix, and then try to find a stabilizing terminal controller. And depending on this terminal controller, you try to construct your ellipsoid. I don't think I can tell you now a general way to check the positive invariance.
Well, it's a difficult problem. I'm just curious if you have some kind of practical shortcut for that. Okay, good. The second question is, why was there only around 10% reduction of the runtime, even though you have significantly reduced the number of full NLP problems that you saw. How would you explain that?
Yeah, I think the computational overhead mainly results from shifting operations, and like you have to first you construct your feasible or your candidate active set, and maybe it's possible to implement it a bit more performant, but it's computational overhead. And of course, you do not always have the case that you find a feasible solution for the simplified problem, but often, or in some cases, you also have to resolve the original optimization. So you have two optimizations in one time step.
Right. And related question to that, all your reduced NLPs are only equality constraints, right?
So you mean in the results section? These are the number of solved full NLPs. So these are the original NLPs.
Right, but the 185 row and so on, those are just NLPs with equality constraints, or half of them are with equality constraints and half of them are full, or how to interpret this?
No, these are 185 NLPs with equality and inequality constraints. So
okay, but some of your NLPs only have equality constraints. Is that the correct statement, or did I miss something?
These are the simplified NLPs.
Yeah, those simplified. And that's exactly where I'm heading to. Isn't there some kind of tailored NLP solver which would work very well only for equalities? Would that help? Are you aware of anything? And again, I'm just curious. I don't know the answer myself. I'm curious.
Right now, I'm not aware of one, but it's of course a useful hint, I think. So to look for a solver dedicated for equality constraint only.
Right. Okay. And the final question is exactly about the size of the disturbance. So what did it represent physically in your helicopter system, and how did you control the size of the disturbance in your experiments?
It's not real experiments. It was a simulation with a model of the helicopter testbed. So we don't have this helicopter testbed. It's just a simulation experiment. So
and then I presume you define the range for the disturbance and then use some uniform sampling from the
random disturbance added to the next initial state. So
okay, that explains. Thank you very much. Anybody else? So thank you very much, Raphael, for your presentation. And with this, we are done with the first part of our schedule for the workshop. I would like to thank all of our online viewers for their attention. We will continue, if I'm not mistaken, at 1 o'clock. Is that correct? 1:30, yeah, 1:30. That's correct. And it would be 2 presentations from the Slovak Technical University. So everybody is welcome to join back after the lunch break. Thank you very much and guten Appetit.